the Earth into two sections. We have the lighter section, which shows the areas that can see the moon at the moment. We can see the red eclipsed moon. It's directly over the Indian Ocean at the moment, and we can see the half of the world there that can see the moon. The other half, the darker area, that is where the sun is at the moment. So North America, for example, in the middle of the day, with the sun in their skies. So this shows the boundary between the nighttime side of the Earth that can see the moon and the daytime side of the Earth that can see the sun. But if we look at where these two zones meet, we can see that there is a very narrow strip where people can see both the moon and the sun. This is that very sort of narrow light strip that runs between the moon side of the Earth and the sun side of the Earth.
But does that mean they're up at the same time?
Right, so this means that if we look at London, for example, we can see that London right now, the sun is setting on one side, and on the other side, the moon is rising. The moon is coming up. And of course, this does need some thinking about, because how come you can see the sun and the moon at the same time? Because we know that the moon and the Earth and the sun are aligned in space. We know that the moon is completely within the Earth's shadow. So if you're on the nighttime side of the Earth, if you can see the moon, it should be impossible to see the sun. So how come it is possible that you can see both objects at the same time during a total lunar eclipse? This is one of those curiosities about a total lunar eclipse.
Are we going to let them know with that diagram?
And okay, well, it all comes down to, we talked earlier about refraction, about how the Earth's atmosphere bends light around it. This is what lights up the moon during a total lunar eclipse. It's the Earth's atmosphere bending the light around the planet and sending it towards the moon. But refraction also plays an important role when we look at sunrise and sunset and moonrise and moonset. Because the atmosphere is bending light, when we look at a sun setting, those final moments before the sun disappears below the horizon, we are in fact looking at a sun that is already below the horizon for us. The sun is already below the horizon as we look at it, but we still see the sun because the Earth's atmosphere is bending and refracting the light towards us. We can see on the diagram on the screen at the moment, we have two images of the sun. We have a true position of the sun, which is below the horizon. We shouldn't be able to see it, but the refraction of the Earth's atmosphere bends the light and bends it round to our eyes. So as we look at it, it appears to be above the horizon. Now, during a total lunar eclipse, looking in the other direction, the same thing is happening with the moon. When we see the moon set below the horizon, we see the moon lingering for slightly longer than we should, because the Earth's atmosphere is bending the light towards us and keeping it visible for longer.
And that's got a name that I can't pronounce.
Right, this has got a very difficult name. This is called selenelium, and it is the phenomenon when you can see the sun and an eclipsed moon at the same time. Selenelium. It is, I have to say, it is a very rare word, and it doesn't appear, for example, in the Oxford Dictionary of Astronomy. Well, you now know the word selenelian, so you are now one up on the Oxford Dictionary of Astronomy. And of course, we should say that this is true not only at eclipses, but anytime we see a sunset or a sunrise, and anytime we see a moonset or a moonrise, we're actually seeing these objects long after we should, after they should have disappeared below the horizon. We should also just say once again, of course, that the diagram we're looking at here of the Earth and the Sun, again, this is not a scale